These days, we hear a lot of buzz surrounding zero knowledge proofs, especially in the world of crypto. More and more coins somehow, some way incorporate zero knowledge proofs. So it started with Zcash. Now we have Monero. Well, privacy coins typically includes include zero knowledge proof, but we have also usage of ZKPs in layer 2 scalability solutions and other things like succinct blockchains. So yeah, definitely there's a lot of things around ZKP. So I wanted to take some time to do a recap of what's the current state of ZKP is, the current state of ZKP, especially since recently we have the release of Hello 2 through the Zcash NU5 upgrade, network upgrade, so network upgrade number 5. And this upgrade uses Hello 2. And Hello 2 is also going to be part of Filecoin. So yeah, it's seems to be the latest development. All right. So what do we have? So let's start with a short recap of what ZKP, what they are, what they can do, and what their purpose. Then we can talk about a little bit of history. So the first ZK Snarks, and then now we are talking about ZK Stocks. And then we can talk about Hello 2 more specifically. And finally, we can do a little bit of a little bit of coding, but just more like reviewing some example. So, example, this example is something I made yesterday, and there's a whole video over how to do it from scratch. But this is not the point of this video, of course. In this one, we're just gonna look at the code and get an idea of how we would implement a simple circuit, a simple program, and so not much coding and not much math either. So this should remain fairly high level, and it's a discussion more about what we can expect from ZKP from non-technical perspective. All right, so let's get started. The first point is what's ZKP, and what can we do with it? So the ZKP is a very general idea. It's the idea that if you have a problem, not a problem, but if you have let's say a problem, if you have a statement which is usually expressed as an equation. So, for example, you have an equation, and the one we have is this one: x cubed plus x plus 5 equals 35. So it's an equation that has one variable, x, and we want to show that we have the solution to this equation. So x would be our hidden value. So it's our secret. And we want to show that we indeed know that value, the suitable value for x. In this case, is actually 3. So we know that if x equals 3, then this equation is stands. Right. So we want to show that we know that 3 is a solution, but we don't want to give the value to out. We want to keep the value for ourselves. So it's a bit of a pickle. It's a difficult problem, because on the other hand, the person who receives our claim, our statement, has no reason to believe us. There's no reason for them to think that we indeed know that x equals 3 will work. And in a more complicated situation, you could imagine that this one is not this simple equation, but it could be a hash function. So it would be that, for example, the function here is SHA-256. So we know that if we know the input to a SHA-256 hashing function, such as the result is something that is stored in a database. So, for example, if it's not a shell, if it's a bcrypt function, that's the function, that hashing function that is used for keeping passwords in the database, then it would mean that we know the password, such as the password is the one that was used during registration, because that's the one that was hashed to the value that is stored in the database. So the problem here is much harder, right? It's not something that we can trivially solve by finding the value by going one by one. So indeed, showing that we know the value of x, such as bcrypt of x equals some hash value, shows that we know the password. But also, we don't want to give our password. If we give our password out, then there's a risk that the password will be stolen. So here comes the value of this one of the values, one applications of ZKPs. There are many others, and that the interesting part is that you can find hundreds of different usages for ZKPs, and the point here is that any expression that is deterministic, and so an expression that is really a function can be turned into a ZKP. Of course, there are some issues. I mean, if the expression is very complex, then there's issue that the proof could be very large, and also that the proof can take a really long time to make. But these are implementation issues, which are getting solved little by little, and we get better. They get better and better by finding better proving systems. But theoretically speaking, the problem remains the same. Right? We have a statement, and we want to show that we have an input to the statement that fulfills this condition. And one or many of the terms of the equation could be parameters. So we know, for example, that if it's a hash function, we don't want to build a dedicated system just for one password. But obviously, we want to have some flexibility and say that it's the hash of the secret that is equal to some parameter. In this case, it would be the hash value of the password for that particular username. And here, the parameter would be this 35, right? So if, for example, we want to change that, we should be able to have x cubed plus x plus 5 equal, let's say, 91. And then x will be a different value. And maybe actually x is not a possible value, because here x has to be an integer. So that's the idea. And the first solutions that were out there, they were called Zk Snarks. So Zk Snarks are the only problem they have. It worked very well, but the first Zk Snarks were a bit slow. They're complicated, complex to build, complex to verify, and also fairly large. So they was not ideal. These are the ones that. But it was already groundbreaking, so it's natural for the first version not to be super, not really perfect. But that was the one that was the initiator of the trend, and that was included in the first release of the network Zcash called Sprout. Then the protocol was further improved with a different new family of Zk Snarks based on another proving system called Growth 16, and the new proving system was much more efficient. It led to a much smaller proof, faster proof. Everything was better. So sapling the upgrade to this protocol is the one that is currently in place. And it's definitely better in all perspective, in all metric, than Sprout. The one thing though that remains problematic with Zk Snarks is the fact that there are two issues basically. The one issue is that there is some kind of parameter that is built specifically for the problem. So if you have this equation, you will need to generate a set of parameters that would only work for this particular problem. If you have a different equation, So if for example you have x power x squared instead of x cubed, you only change one term, then these parameters will not work anymore. So you will need to generate new parameters. Right? So that was one issue. The set of parameters is dependent on the problem, on the statement. And the second one is, which is much more critical, is that in order to generate that parameter set, you need to choose a random value. So any random value would work, nothing special about that. But then you need to destroy that random value. You need to make sure that nobody knows that the value that was chosen for the generation. Because if somebody, even if it's yourself, if somebody knows that value, he can create fake proofs. So he can create proofs that essentially will prove that that he knows the solution to this equation, but indeed, but in fact, he does not. So the proof is a fake proof. If you verify it, you will verify that it seems that the proof is correct. Everything will go through, but actually, it has proven nothing. The guy doesn't know X. And if this statement is the base of your crypto coin, it means that he was able to create coins, or he was able to make a transaction that is actually completely invalid. Right? The statement of the transaction for Zcash essentially enforces the rules of proper transaction, that you're not creating money, you're not creating sending to an address that is you're not spending for an address that is not yours, and etc. So if you can create a proof of that, but the proof is forged, is wrong, you actually can spend from an address that you don't own, and you can create coins. So that is very, very important flaw. It's a very critical flaw. So it's very important that actually nobody has knowledge of of the random value that was used to generate the parameters. So there are two problems. So the second problem was mitigated by going through a ceremony of basically combining the input of several people, like more than 100 people participated in providing some random value, and the result is obtained by mixing all these values together. So if only one of these people remained honest and did not save their copy of the random value, then the resulting value is not retrievable. It was essentially destroyed. So only if these 100 or more people colluded and all share the same value together, and then to rebuild the secret, then that protocol is a failure. So more likely than not, that didn't happen, and we can be fairly safe in the assumption that nobody has that secret value. But the first problem remains that if we somehow want to change the protocol, if we want to do something else, there was a bug, for example, and we have to fix it, then we would have to go through the same ceremony, because the statement will be different, and the parameters that were generated are no longer valid. So I have to go again and do the ceremony again. So this is a fairly big problem. But the advantage, though, was that the proving system was very good, it was very fast, and it created proofs that are actually independent from the size of the problem. So you could have very, very, very complex problem, like millions of steps, but then you could have a tiny proof at the end. So with Hello, we kind of lost some of that. We don't have the ability to have a fixed size proof. The proof is scaled with the size of the problem, the number of steps for this statement. But we have no trusted setup. So the value that we talked about is called a trusted setup, because we have to trust that the creation of that value was performed correctly. So we don't have that anymore. But we have other problems. But the general consensus is that still we can improve on the size of the proof and on the speed of the proof. There are optimizations to be made, and it's therefore worth going to a system which gets rid of the trusted setup. So that's pretty much where we are today. Today we have several proving systems. We have I know 2 or 3 of them, and they all take care of the trusted setup. I mean, they got rid of it, but they have different trade-off. They have some are faster to generate a proof, some are faster to verify, and so nothing is really perfect. And Hello has some unique advantages, but it's still a fairly young system. So we'll see where it goes. So this is what we have today. So let's go to the next point. The next point is if you want to use Hello, what are the things that you need to be, what you need to know, how this stuff works. So we have this code here that implements the proof for this statement, right? Xq plus x plus 5, and then we can see how this is actually done in practice. So you can see the code is not for what it does. The code is fairly long. I have to say that if you were coding this in just a line, right, it would be like a couple of lines. It would be x equal 3, and then xq plus x plus 5, and then is it equal to 35? Yes or no? So we are not there. We're not able to generate a proof by only running this stuff, by not only running the statement. There are proving systems are a bit more longer in existence, right? So they and they have worked on facilitating the generation of the proof. But Hello again is fairly new, so we don't have that yet. So we have to write all this code, right? And it's also a blessing in disguise, because we would know a little bit more how these things work. A little bit like if you want to learn programming, you benefit from knowing how assembly works. And this is going to be like the assembly of ZK proofs of Hello 2. So that being said, what are the pieces that we have to do? So let's look at the main code. Right? The main code looks fairly standard, because we have the pieces, the parameters that we know. We're not surprised here. We have x, so everything is going to be fp. Fp is an integer in a field, and p is the size of the fields. Just need to know that p is very large, so it's not like infinite, of course, right? But it's very large. So for all intents and purposes, you have plenty of room. But they are integers. And if you go negative, you're going to have large numbers. So if you do inverse, it's also a bit tricky. Anyways, the point here is that everything is an integer of this field, of this set of numbers. So we start with having our x equal 3. We know our constant is 5, right? The x cubed plus x plus 5 equals 35. And our parameter, the right hand side, the result, we want it to be 35. So we have actually one example of each type of variable. So x would be our advice, and it's called advice. Not really sure why it's called advice, but it means that this is a value that you want to keep secret, and any value that is going to be computed from another advice, from another secret, is also going to be secret. Right? So these are going to propagate a little bit. Constant is something that never changes, and the result here is our parameter. So this is called an instance variable. And basically, an instance variable is is a public parameter. So 35 is something that you can change when you instantiate your proof, when you want to create your proof. So we have that. Then we have our circuit. So we'll see later what's that circuit and what it does. And then once you have that, then you say, these are my public inputs. And I want to create a proof. So this is a mock prover, but this is basically the same idea as later. Right? So this is a real prover. And okay, so we can actually just skip and see here how the proof is created. Right? The proof is created first by generating a verification key and a proving key based on the circuit, right? And the parameters here is just the kind of the size of the determined by the size of the circuit. So you want to have a number here that is not too large, because then there will be a lot of wasted space, and a lot of the space of your circuit will be empty. But if you choose a number that's too small, and there's not enough, it's kind of like the memory, if you want. So we create the verifying key and a proving key. Then we can create a proof and write the elements of the proof into the transcript, right? And then we close this transcript. That gives us the proof. So essentially, the create proof here drives the machinery, and the transcript is the file, the output file. That you close the file, and then you have your proof. And when you want to verify, then you do the opposite. You create a verifier. You put a reader on your proof, and you call this function verify proof, passing the verification key, and again your public parameters. And if your proof is correct, then it's going to be okay. Right. So of course, in the second section here, when we verify, we no longer have access to the circuit. We don't have this X. Right. So the main point here is that verification can be done without knowledge of the circuit, just by having the verification key. Okay. So now the question is, what's this circuit about? So the one thing to know about these proving systems is that they are actually very mathematical in nature. It's behind. You are basically building a massive set of equations. You have what happens is that you have this this statement here, right? Sorry, this statement here. But you can't just like say this statement is what you want to have implemented. As if you are building a program. If you're building a program and the program evaluates this statement, you are going to be doing it in smaller steps. The CPU, even though it's very, very fast, it can only execute very basic operations. It executes basic operations very quickly, right? So it has ability to do additions, multiplications, etc. So you have to take this expression and then break it down or translate it in a way that the CPU understands. And that's typically done by a compiler, right? You write this in a high-level language. A high-level language transforms that into assembly. Assembly becomes binary code, and binary code is executed by the CPU. Right? So most of the time we don't have to do it by hand, right? We know that we have good programming languages and compilers that will understand this and then automatically generate the proper code for us. With Hello, we are not at this stage, right? We can't do that. So we have to actually do the steps ourselves. So the reason why it's called a circuit is because we are fairly close to the point where we are laying down components on the circuit board, and each component is going to do some operation. We can build a chip by ourselves. We can build custom chips. So you can think of it also like when you are mining, right? So your miner, you can use a CPU or you can use GPU. But if you want to be super fast, you're going to create your own chip that is dedicated to a really specific set of instructions. The one that is for proof of work. So kind of the same idea here. We can create our own chip that implements some of the logic we really care about, and use these repeatedly and assemble them and use instructions on them, right? So the chip that we're going to make here is a chip that has the ability to do a multiplication and an addition, because we know we need to multiply here to go from x to x squared to x cubed, and then we need to add values together to have this term here. So with these two instructions, we can build this statement. These instructions are actually like fairly basic, so you probably don't need to do that. You can use a standard implementation. But for example, we are pretending that we have to build our chip ourselves. So we define an instruction set, and this instruction set has these functions, right? Multiplication. Basically, this is your API between your integrated circuit, your chip, with the outside. So this load private is where you're taking input from the outside and putting into a register, but this is for a secret value, and this is for constant. And these are the operations you can do. And the last one, expose public, is where you take the result and you export it out so that we can check the constraint is matches the 35. The result value is matches the 35. So this is your API, your chip API. So this is one thing. And your chip then has to implement that. So again, these operations, up to you. You can use these. You can make more complicated ones. And then you implement them, right? So the implementation actually is where you start interfacing with the proving system. Here you interface through this something called the layouter. So the chip itself is like a high level abstraction over the underlying system, which is again this massive, gigantic set of equations, and each what happens is that each row and column, each cell, contains a value, and that value propagates some intermediate result. So, for example, here, let's say that the first row would be, we would put x, right? We put x there. Then we want our chip on x and x, right? First row, first column would be x. First row, second column would be x. So we want to preload that here. And then we ask our chip to do such that the second row and first column contains x squared, right? And for that, we want to we will say that there's a relationship between this value and the values of these two cells. All right, so all the values in this matrix will have to fulfill a certain set of conditions, and if you know the proper x, it will be very easy for you to actually fill the entire thing, because if you know the starting x, then you know that the condition that is here just expresses that this value is a square, is the product of these two cells. So you can just multiply them. But if you don't have x, if you don't have any of this stuff, and you only know the conditions, then this is going to be a very, very difficult problem, because there's hundreds or thousands of millions of these equations, these equality conditions, and to find the value that matches them is nearly impossible without having the starting point. If you have the starting point, then you know everything. If you don't have the starting point, then you cannot find anything in the middle. And So the implementation of this multiplication guy here is about dedicating a portion of your matrix. So that's why we use regions, and say that that particular region advice column blah offset 0, column 1 offset 0. So this is row 0 column 0, row 0 column 1. This is going to be A and B, and then the product A times B is put into column 0 row 1. So these are kind of relative coordinates, but you can recognize that this is the same structure as here. You have A, B, 0, column 1, row 0, and then next one, the product x times x is in row 2, column 0. Alright, so by declaring this kind of things here, you're telling the layouter, so this guy here, which portion of the circuit, of the board, if you want, has to be taken by these values, and which value you want them to have, and what relation you want between them. Right. So, and when you do that, it's actually declaring the usage of your real estate of your big matrix is kind of like the surface of your board, and how you use these little regions is going to be up to you, because then you put instruction. You're going to call these functions in the main program, and then this will allocate little pieces of, like this is of 2 by 2, or this example is 2 by 2. You will allocate little regions like for these instructions, so multiplication, addition, and other. And then the layouter will do its best to use the least amount of space, because you also want to have your resulting set of equations to be as small as possible, so that your proof is not going to be extremely large. Right? Maybe it could be the smallest possible. So we can, once you have these merge and add, right? So we have implementations for these ops. We can see how it's used in the main in the circuit. So the synthesize function of the chip of the circuit, right? So the circuit uses chips, and the chip has this programming interface where it exposes basic operations. Right? So then I can go, we can go and then actually use this and chain the stuff together to implement our expression. So we start, we are loading the private value x into the chip, then load the constant, and then we do x squared, x cubed plus x, and x cubed plus x plus 5. And then we recognize that for x squared, well, it's the product of x by x. Right. So these guys here, fairly verbose. Not gonna lie, it's a lot of things to write for such a simple expression, but it's still fairly straightforward. It's not it's not a very complicated thing to write. And then finally, the result here, then we expose that so that it has to match the public value, the instance variable. So your synthesize function, which is the crux of your circuit, defines the statement. Right? So here we only use one chip, but it's very possible to use more than one chip. Right? Use different chips for different operations. And your circuit has a set of input pins, if you want. We know that we need two pins, two advices, basically two columns to store intermediate values, right? Because we have binary operations. So we have x times x, x plus x, right? So we need two of these columns. We need one column to store the parameter, and we use one column to use the fixed constant. So this is the definition of our circuit, the shape, if you want, and this is how it executes what instructions it executes through the usage of the chip. Right? So the circuit and its configuration, I think at this point it should be fairly and easy to understand what its role is. So now we go a little bit lower. We wonder how we can implement the logic of a chip. So we saw that the chip itself, right, has this part here, but this part here only defines the usage of the region, and this stuff here, which is a times b, a plus b here, and a times b here. This is Rust, right? This is not something that is part of the constraint of the set of equations. This is not something that is natively understood and translated into an equation. So here I could have written something arbitrarily complex. Right? I could have used like time or whatever. So obviously, whatever I put here is not going to be always possible to do on the set of linear equations. Right? So the point here is that this guy here though should reflect something that can be executed by the chip. Right? And then you see that there is a part where we configure our chip. Right? We have a config, and this config is a config of the chip. Right? It's not a config of the circuit. It's a config of the chip, and this configuration here is very much the same though, because we have one chip, one circuit, right? So we also have the same structure, more or less. Okay, where is this? Yeah, so we have also our two advanced column. We also have our instance column, but now we have these selectors. Right? We have these two particular columns, and we can see what they are used for. So the chip itself, right, is where we have to define the rules of our add and multiplication in terms of relationships between cells in this huge matrix. And the way we do it is to say that if you want to lay out where if I put x and x here, x and y here, and then I want to result x times y, so the product of this value here, if there's 1 on this cell, then I can write it as a particular expression as a gate. So gates are, right, when we have in the past, when we were talking about the old proving systems, each of these rows really had one type of constraint hard-coded. Right? It was always that each row had a constraint where, let's say, this column times this column plus this column plus that equals 0. So the shape of each row had exactly the same constraint. And then you could vary the stuff that you wanted to enforce between rows by setting some of the columns to 1 to 0. So essentially we had what we call a selector. So some of the columns here were essentially selectors, because if they had a value of 1, then you would select or you choose a particular type of constraint. And it's going to be much clearer once we go and use it for our own purpose. But this is inherited into our design. So when we create our own gate, so we have the ability to create our own conditions. We want a condition that if we apply that chip, that gate, so we use the chip, so we use that gate, it's gonna express this, it's gonna put the same condition over every time we use that gate. Right. So we want a gate here which combines addition and multiplication, and our design for that, and there are other designs possible, of course, that if the column here is the value here is 1, then we want to have a multiplication. We want this guy to be the product, the next row, the column here on the next row should be the product of these two values. But if the the M is 0 but S is 1. So we have these two columns are selectors. If this column is 1, then we want the next row to be the sum instead of the product, right? And we will express this relation between all these 1, 2, 3, 4, 5 cells as a bunch of polynomial statements. So bear with me, we're gonna do it. It's not gonna be very hard, promise. And let's take a look at how this is done. This is basically done by the chip configuration, where we get the constraint system, right? So we have something that at least allows us to operate on the Halo 2 proving system. So something that allows us to define the constraints locally around that gate. So and for multiplication at gate, what do we do? What do we have? We have left-hand side, which is the advice column, first advice column. The right-hand side is the second advice column, so the one next to it, and on the current row. And the output is the first column, but on the next row. So you can recognize that, you probably recognize that this is very similar to this, right? Advice 0, advice 1, offset 0, offset 0, and then out is column advice 0, but offset 1. Right? So the shape basically 0, 0, 1, 0, and then 0, 1. Right? So this is the same as here, 0, 0, current 0, 1 current, and then 0 next. Right? So this is exactly the same. It's a bit of a pity that we have to write it again, but in different form. But really, it's the same idea here. And then we pick up the selectors. We pick up the two columns are added, and our condition for this gate here is a fairly straightforward one, actually, because we know that if S_merl is not set, if it's 0 and we don't want a multiplication, then we actually don't want any multiplication condition on L left-hand side, right-hand side, and output. But if S_merl is 1, so if this guy is not 0, then we want this term to be 0, right? So since it's a multiplication of two things, and the condition is that this guy has to be 0, we know that one of them has to be 0. So either S_merl is 0, in which case we don't care about this, or S_merl is not 0, and then we must enforce, the constraint system must enforce that left times right minus out equals 0. In other words, that out is equal to left times right. And then the same applies to the add. So we have actually two constraints here. We have 1 and 2. But this time on the add selector, if the add selector is set to 1, then we want this condition to stand. We have left plus right equal out. And we know that because we don't set these two selectors at the same time, that would be impossible to, that would be that will lead to an invalid constraint system. Then we will never have a problem, right? We only set it as add. We set it when we want to perform an addition, and S_merl, with sector S_merl, is enabled when we want to do a multiplication. And by default, these guys are not set. So if both are not set, then there are no conditions. This gate enforces no condition, and left-hand side and right-hand side can be whatever they want, which is useful when we actually load we do the other operation, when we just load a private value, or we load a constant. Right? So not all rows of this matrix will have an operation. We have an instruction addition or multiplication. So some of them will have 0 and 0. So and then we have we have it. This not much. This is all there is really to the. I mean, at this level of understanding, we have seen how we define the custom circuit, and how we define a custom chip, and how we did implement a custom gate. So this is pretty much all the important concepts around Hello. And you can see that it's really powerful actually, because the chips that you define, these little constraints that you define, you can repeat them at different parts of your circuit, because the expressions that you have here, they are relative to a region. And then if you have things that bridges between different areas, and then there's a way to express that, it's also going to be taken care by the framework. The Halo 2 library is going to pick up all these relations and then add the constraints that also enforces that between regions there are some cells that must be equal. Okay, so but that's all we have for today. Although I think it's enough, I think, for today. It certainly has everything of that is needed to build a fairly small circuit. But even the bigger ones, they are, of course, they're much more complicated than this. They incorporate more chips, more gates, and more complicated layouts. But the idea is not extremely different. So we have seen that all the important concepts of Halo 2 proving system. All right, and so that's it. That's all I have for today, and I hope you like it. And if you want to try, I will share this code on GitHub, and I encourage you to give it a try. It's definitely quite interesting. But that's it for today, and I hope you have a great day.